Today I'm going to talk about how to parallelize NDSolve. I'm going to give you a description of different methods that can be used. I'm going to give you an outline of the method that I've chosen, and then I'll give you some examples of some applications. So this came out of some discussions we were having for the new compiler, where we're looking for ways to parallelize code, applications in Mathematica and application areas. So one candidate is NDSolve. It's widely used. It has many application areas. It has a fairly modern design. It solves computationally intensive problems. It's got a rich set of accurate solvers that are well optimized. And it uses this vectorized framework for solving differential equations, which is a good candidate for parallelization. So there are several approaches to parallelization. So the first one is to actually parallelize the arithmetic that's inside the method. So we do things like multi-threading, the vector arithmetic, the function evaluation, and multi-threading the linear algebra using some special purpose libraries. The advantage is that it improves all methods. You know, any method that uses a vector framework will get an advantage from multi-threaded vector arithmetic. The disadvantage is that the thresholds are reasonably high. So you need a system with like 1,000 or 10,000 equations before it can be multi-threaded. So another way to parallelize is to parallelize across the method. So the method itself inside will farm off to different threads or different processes. So there's a large literature on parallel integration methods. The drawback is that we often need special methods to work better in parallel, like a standard Runge-Kutta method or something like that. It's not immediately parallelizable because in its internals, each stage is coupled strongly with the stage before, and it needs to work in a serial fashion. So we'd have to implement a new set of methods that would be parallelizable. And these would only work for specific types of problems. Okay? So a lot of work for a little gain. So another approach is to actually discretize the actual problem that we're interested in. Now, there are many methods available. Some work in the spatial domain, and some work in the temporal domain. So the choice that I've made as a first approach here, which seems to fit well into NDSolve, is a parallel in time discretization. That's the method that we're going to consider. So solving NDSolve, each NDSolve method, or solving an initial value problem is like a Mathematica nest function. It's inherently serial. So each application of the function on the one before has to be done. To get the next value, you have to apply it over and over again to the same value before. So the idea is here, instead of solving for n points, we're going to subdivide n into little pieces. We're going to compute a different function, g, instead of f, okay, over some subdivided grid, and we're going to iteratively correct these points in order to converge to f. So the method that I've implemented is called the Parareal method. It's one of the most widely studied parallel in time methods for solving differential equations in parallel. It's introduced, it's quite recent, it's introduced in 2001. There's been a huge amount of study on this method, the properties of the method, when it gives good results, when it doesn't give good results, the numerical stability of the method. It's a very general purpose method, which is good because then we can get a wide set of problems that we can apply it to. Since the method was invented, it's been discovered to be what's called a two-level nonlinear multi-grid algorithm, multi-grid reduction in time, and multi-level algorithms are extremely efficient. It's designed in its origins for exascale computations. That's really big computations, Fortune 500 companies, people solving extremely large problems. Okay, so that's the motivation for that method. Now, it turns out that this fits extremely well into the existing NDSolve framework. It works well with one-step methods, of which NDSolve has a wide variety. It uses existing tools for concurrency, so that's MathLink, Mathematica, and subkernels and parallel computing. And it uses very few parallel directives, parallel evaluate, parallel table, distribute definitions. So here's an outline of the method, how it works. We want to solve this initial value problem over a time interval. So we'll subdivide this time interval into little pieces where the number of subdivisions is the number of processes or the number of parallel computations that we're going to be doing. Okay, so we have a time interval, say 0 to 10, and we'll chop it up into smaller time slices. By chopping it up into these uniform slices, that's a uniform distribution of work in parallel. Okay. Now, the Parareal method works using two numerical integration methods, not one. It uses a low-order cheap method, that's this G method here, and it uses the original method that we're going to compare against, the so-called fine method. But the point is, the cheap method that's done on to a lower accuracy is very efficient. That's the one that's done in serial. So we're replacing an expensive computation in serial with a cheap computation in serial. And then we're going to do the expensive computation with the original method that we're interested, but we're going to do it in parallel. Okay? So we do a big serial step, we do a parallel step, and then we go and iteratively correct until we get some sort of convergence. So here's a mathematical outline of this thing. This is what the standard integration would be like with the standard integration method over the grid that's been discretized. So the Parareal iteration is this. It starts off with a coarse solution using a lower order integrator instead of a higher order integrator. Then it goes and uses the higher order integrator on the solution that was found here, but it does this bit in parallel. Then it goes and forms a correction, and it goes again and does another serial computation, but using the improved solution that was found correcting from the parallel computation. Okay, and then you just go and iterate this over and over and over again until convergence. And hopefully, if the number of iterations that you're doing is small compared to the number of parallel processes that you have, it converges very quickly, and you get a good speed up. So I did a little movie to show you, but it's not comparable to Todd's sailing video that he just showed, so I'll skip that and move on to something a little bit. Move on to something a little bit. If we have time at the end, I can show you the little movie. So a bit about the design of this method inside NDSolve. So there are several ways. The traditional way to do it is to write it as like a driver method. So this thing discretizes the mesh, and you have to write some methods. And very often it's done with a simple fixed step size explicit method or something, which is not even good for a stiff problem, something like that. So we really wanted to incorporate it into a nice way inside NDSolve. So a driver method would be something like parametric NDSolve does at the moment. It does some kind of processing on top for the different parameters that it needs to solve, and then it goes and calls NDSolve for each value of that parameter. And that's the kind of design that's done conventionally. So this has got several limitations. If you have a really long time integration, like up to a time 1,000 or 10,000 or something, the convergence is going to be very slow, even if you've got like 100 or 1,000 processors, something like that. So we're going to flip things around. We're going to make the Parareal method go inside NDSolve. So it's a time-stepping method, and it's not going to work on the whole integration interval. It's not going to work from, say, t goes from 0 to 1,000. It's only going to work on a little piece at a time, say 0 to 10, and then 10 to 20, and 20 to 30, 30 to 40, et cetera, et cetera, et cetera. And then inside each subcomputation, it will still be doing stuff in parallel or whatever, but on a smaller integration region. And the important point is here, when you're having event-driven computations, you don't know where some event is going to happen. So often you write in NDSolve like t goes from 0 to infinity. Now with the Parareal method, you couldn't discretize an infinite time, no matter how many processes you have. But if you break this down into time units, small time unit blocks, you just go 10 at a time, then eventually you'll get to some event. It doesn't matter how long it takes or whatever. So that's the advantage of having it sort of flipped on its head and having the Parareal method inside NDSolve. And this is a little bit similar in spirit to some of the actual methods in NDSolve. So the main thing that had to be done to make this method work efficiently is to change the main data structure in NDSolve. So NDSolve has what's called a StateData object. When NDSolve starts up, it converts this problem, it does an analysis of this problem, and it sets up all sorts of things it might need, like index reduction, initial conditions, all sorts of things that are going to be needed, and it makes this big data object. Then it's going to use that data object to carry it along from step to step and then update the information inside that. Now, this data object is quite big and quite heavyweight. In the Parareal method, we're going to need several of these data objects. We're going to need a main one for the Parareal method. We're going to need another one for the serial method. We're going to need another one on each subkernel for each of the parallel integrations. So we're going to make copies of this thing. We need lightweight copies of this thing. So I've changed this data structure. It's much similar in spirit now to association. It's what's called a raw expression. Okay, it's a very little lightweight wrapper around a big C data structure. And it's only converted to this big bulky form that we saw here when it's sent over MathLink. And that allows me to continuously update and reset this, this data structure without having to worry about this big bulky representation. So it gives me kind of a much more lightweight way of working with this data structure. Now, the parallel primitives, there are really only two parallel primitives that this method uses. It has to launch and close subkernels for the method to work. It has to send the main NDSolve object to each parallel kernel for the method to work. And then at the end, it has to clean up after itself. The actual main computation is just a simple loop using parallel table. It calls the NDSolve parallel stepping method on some grid interval with initial conditions and corrections here. So it's a very simple, this is designed to work with vector data, and it's a very simple call to parallel table. The important thing is to keep that thing very simple, because that's going to be called every single time you do a parallel computation. Calling the evaluator is quite expensive compared to the actual time that we're going to spend doing the integration. So I've set up the data to be, in order to make this as simple as possible. Just a quick thing about NDSolve. Another thing that was needed in NDSolve is a finalize method. So we have a method initialization that sets up things like method coefficients, workspaces, data structures that the method actually is going to need. Here we're going to need a finalize method because we're going to go and need to clean up afterwards. We're going to need to close kernels that have been launched. Or if the kernels are persistent, we're going to go and need to clean out data that's been left in each of those subkernels. Okay, so we're going to need a finalize step inside NDSolve. Okay, so this is the basic method, how it works. NDSolve, it does its equation processing. It gets to the Parareal method. The Parareal method goes and initializes data, sets up subkernels. It initializes the submethods, and it sets up data structures that it's going to need. And then it gets to the actual iteration method. It goes and calls a low-order method in serial, and then it goes and calls higher-order methods in parallel, and then it goes again after another iteration, working out a corrective step here, and does another serial computation, and so on and so on and so on until you get convergence. And then it gets to the end of this particular subgrid computation. If that's the end of the time integration interval, then we're done. Otherwise, it will go back and do the next chunk of computation. Okay, so this part goes back to itself. And then eventually we get to the finalized part where we go and do the cleanup, and then we process the solutions to the interpolating functions in NDSolve. Okay, so the speed up of the Parareal method, it depends on the cost of solving in serial, the cost of solving in parallel, the number of iterations that are needed for convergence, and also the number of parallel processes that are running. There's also some kind of latency and data copying and that kind of thing. So here's a very simple example. This is just a kind of trivial equation here that we're solving over a specific time. It's just the time that NDSolve takes to solve this using an explicit Runge-Kutta method. Okay? Now, this is the Parareal method. The syntax for the Parareal method, it takes a serial method, and it takes a parallel method. Now, in this case, they're both the same. The order of this method is going to be lower than this method. This is going to be a higher order method, a lower order method, because in serial we're solving using lower tolerances. We're telling it, so maybe solve only to 10 to the minus 3 or 10 to the minus 4. And so the method automatically will choose a lower order scheme here compared to the higher order scheme. Now you see this is quite expensive compared to 0.02 that we had before. But the point is, a lot of that overhead is not actually the method itself. It's actually launching and closing the parallel kernels. So if we actually launch the kernels beforehand and then go and call the NDSolve method and then close the kernels afterwards, then it becomes much more competitive. It's less than a factor of 10. For this is a trivial problem that's not parallelizable at all. So this is kind of a worst case for this method. Okay? Now, I'm really trying to get this overhead to be as small as possible so that you can try it. And so within a factor of 10 is OK. I'll be happy with a factor of 5 or something like that on trivial problems as a worst case scenario. Okay? So that's something I spent a long time developing this method purely in serial just to bring the overhead down as much as possible. Now, if you actually look at the computation here, this is the solution of the explicit Runge-Kutta method, and these are the two solutions, one launching the kernels locally and launching the kernels globally. Of course, these are identical, because it doesn't matter if I launch them globally or locally, but I just wanted to check that was the case. Now, the other thing that you can do here is I can call this Parareal method, but I can call it now with high precision. Okay? Now, this is really quite new, the implementation. The whole parallel framework only is like less than a week old that the parallel primitives are working. This I got working on Monday on the plane on the way out. So, you know, don't expect huge things for the first iteration of this method, but it does work, and it gives me a reference solution that I can compare to these two here, and this is the solution converted back to machine precision. And if you compare these digits, you'll see that there's about an extra digit of accuracy in the Parareal method. But they're both within the order of the error estimation. The accuracy goal and the precision goal has been satisfied. That's the important thing here. And the important thing is that this method also works for a high precision reference solution. Okay. So let me get to a PDE example. Now the nice thing, okay, I just need 2 minutes. The nice thing about having this method inside NDSolve is it can leverage off all the things that NDSolve does. So when NDSolve processes PDEs, one of the methods that it uses is a method of lines. It will do a discretization, and then it becomes purely an ODE problem. Okay? So I can leverage off that. I can use the processing that NDSolve does when it sets up this grid to solve this PDE. So here's my Brusselator PDE. And here's just to show you that it does actually work for solving PDEs. So here I've chosen a method that switches adaptively when the problem becomes stiff, and I've chosen that both for my serial and my parallel method. Now, of course, this is going to be a lower order method because the tolerances are smaller, and this is going to be a higher order method. And it does actually work. You can see this, I've actually managed to solve this PDE. But what about the runtime? So I want to show at least one example where I got kind of some speed up with this method, at least even if it's just in its infancy. So here's one for this Brusselator problem. Now it needs a little bit of, if I just call NDSolve with a stiffness switching method, this is a 16-core machine, okay? Then it takes about almost half a second to solve this PD problem. If I call Parareal with the same method for the serial and parallel computation, it takes a little bit longer. So it's no real speed up. 16 cores. This method is really designed for many, many cores, 200,000 something. Okay, so if I can get it to be competitive, you know, for a small number of cores, then I'm doing a reasonable job. But the really important thing is here. So the parallel method is using a stiff solver because this system of equations that it's solving becomes stiff. It has to do linear algebra, stuff like that. the serial method is done to a lower tolerance, and that's not necessarily a stiff problem, okay? So I can use what's called a stabilized Runge-Kutta method in NDSolve, and that's an explicit method. It's an explicit method, but it has a wider stability domain, so there's no linear algebra, there's no additional overhead of a stiff solver. And so the serial computations in this Parareal method are done using a very cheap, very efficient method. And what was necessarily to do before in a serial way using an expensive stiff solver has now been pushed down to the parallel solver. Okay? So I'm using the stiff solver in parallel, but I'm using a much cheaper, much lower order, much more efficient thing to do the computation in serial, and then I'm going and correcting. And I'm already able, even on a machine that is not really designed for, I'm already able to get something that's faster. Okay. So the implications for the new compiler, and that's one of the reasons why we started this project in the first place, is what do we focus on? How do we kind of develop functionality of the compiler? And how does that feed back into Mathematica? So the real thing to take away there is that we should really be focusing on lower order, lower accuracy methods and parallelizing those or making those more efficient. Because that's the thing in the serial step here in this Parareal method. Those are really the methods that are going to give us the biggest benefit. Of course, we should continue to parallelize arithmetic, but we should choose like low. NDSolve traditionally has been focusing on solving equations very accurately, and it has a good set of higher order, reasonably expensive methods to do that. But now if we can push to having a new set of solvers that are very cheap for simpler, lower order solutions, that will benefit this method. So there are some optimizations that I still have to do here. I can save 1 over p, 1 over the number of processes work, because after the first iteration, I don't need the first subkernel. That could give me some kind of redundancy or fault recovery. I have a subkernel, extra subkernel sitting there not doing anything after the first iteration. That's an optimization that I haven't done yet. Other things that the method needs, maybe a better starting step estimate to make the method restarting more efficient. Need to go and reduce the overhead inside NDSolve. NDSolve is set up so that it does a lot of work and then does a big long integration. But it's not so good when I have to do lots of small kind of restarted integrations, which is the kind of things that this method requires. And I also need to be a bit more careful when I set up my grid for parallel computation to take account of discontinuity points and points coming in from events that I haven't quite implemented that yet. But the thing to take away here is even in its form at the moment, it's still quite state of the art, because you just choose the methods built into NDSolve. You just select your method for serial, you select your method for parallel, and it will go and do that. In most of the implementations in the literature, you really have to go and implement your own ODE solvers for the serial and parallel methods. You have to choose the step sizes. You have to do all sorts of things that NDSolve does automatically for you just by calling it within this framework. Because of the richness of NDSolve, we have non-stiff and stiff solvers, things that work adaptively. Now, the method works best for a large number of cores, but because we've flipped things around and put it as a solver method inside NDSolve, we can solve the problem iteratively for smaller blocks of time, which is good for event-based computation. Now, I haven't implemented it universally for all NDSolve methods. Delay differential equations, differential algebraic equations. There are a lot of extensions of this method that can come over time. This is kind of a proof of concept to see that the method actually works and can give us something useful and a good direction for the future. Okay, so I'm finished. So if anyone has any questions, then